Okay, this is the first video on centripetal force. In this video, we'll talk about the main concepts that go into understanding centripetal force. In following videos, we'll look at some examples so that we could further understand what we're talking about. It's important to understand that centripetal force isn't a new type of force, right? Down the road, we'll be introducing different types of force, magnetic forces, electrical forces, things like that. But this isn't a new force. This is really a specific situation, right? To me, it's kind of like when we talked about free fall, because we did work with motion in a straight line, and then we introduced this concept of free fall, and it really wasn't a new topic. It was just a specific situation where we used the same equations we had before. And centripetal force is very much like that. It's not a new force, it's a new situation. Now, it is going to introduce some equations for us, which will help simplify situations, which is very nice. But again, it's not a force in itself. Now, when we talk about this situation, we need to understand uniform circular motion. Uniform circular motion is further explained in the situation that we're dealing with. So when we're talking about centripetal force, and we're going to certainly define centripetal force in a little bit, but understanding this is the start, right? So uniform circular motion is a situation where an object moves in a circular pattern at a constant speed. So it's got to have both parts, right? It's got to be going in a circle, and it's got to be moving at a constant speed. Those are the two things that go into uniform circular motion. Now, we're going to see in some examples, it doesn't have to go in a full circle all the way around. If we have like a car taking an exit and it's, the exit is a quarter of a circle, well, then that's fine. If it's taking that exit at a constant speed, it's still uniform circular motion. We could assume that if it went all the way around, everything would still kind of stay, the applications would stay the same. So we could see things that do, a piece of a circle or an arc of a circle as long as it's a constant speed, and that's fine. So when we say this moves in a circular pattern at a constant speed, there's some things that we should recognize, right? And we're going to look at a video of this in a second, but I like to use this idea of the rotor, which was an amusement park ride, which was and is a ride where you go around and around and around in a circle, and when you go so fast, then the floor can drop out and people are simply stuck to the wall. Right? This is a good example of uniform circular motion because while the ride's going, you're going in a circle, and you're not changing speed, right? You had to speed up to start the ride, so you have to slow down to end the ride. But while you're in the ride and the bottom falls out and you're stuck to the wall, you're going at a constant speed. So here's some examples of that. Now, we want to kind of look at this, and let's say we pick a person, and the other thing I like about the rotors is I kind of recognize it from, going to the amusement park. Lake Compounds used to have one, and they exist in other places, where everyone could kind of stand around and look down on the people in the ride and watch them going in a circle as they're in a ride. And that's one, it wasn't this big where there's rows and rows and rows of people, but at Lake Compound, you could stand atop and look down on the people in the ride. So let's say we're doing that and we're looking down and there's a person, and just for the sake of argument, we'll say there's one person. So there's a person going around, and again, just for the sake of argument, we'll say that they are going around clockwise. So again, uniform circular motion. We have something that's going in a circular pattern, and they're going at a constant speed. All right, sorry about that. So we have this person, and here they are. I'm going to draw them in again. And they're moving clockwise. And there's a few things that we're going to put into writing in a second, but let's go ahead and just kind of think about this situation. Now, this person's going at a constant speed, but they're not going at a constant velocity, right? Velocity has speed and direction, right? How fast are we going in a specific direction? Velocity is a vector. So we can't say the velocity is constant. If we look at the person when they're right here, then their velocity is this way. But later on, when we put this person here, well, their velocity, that's an awful line, but their velocity is this way, right? So we don't have something that's a constant velocity. We have someone that's going in a constantly changing velocity. In this case, the velocity is constant changing only because the direction is changing, right? The speed's the same. They're not speeding up. They're not slowing down, but they do have a change in velocity. So velocity is going this way. Velocity is going this way. Again, if I put them down here, what's their speed with direction? Well, what's their velocity? They are going this way just for an instant, because as soon as they end up here, their velocity is something different. As soon as they end up here, their velocity is something different, right? So, if we pick them at any moment in this trip on this ride, then we can figure out their velocity, and we know the direction, and we can get the speed, right? If we do some calculations, but it's always changing. So that means that if there is a constant speed but a constantly changing velocity, this person is accelerating. So this is a situation where a person's under constant acceleration. So constant speed, but not a constant velocity. The velocity is always changing direction, which means we have an acceleration. Now, if we draw this person, it doesn't matter who we pick one of these people, and now we look at it from inside the ride. So here's the wall that they're pressed up against. Here's their head, here's their body, and their arms are pressed to the side. Now, if we drew a force diagram of that, then we know there's a few forces. Now, this force diagram isn't exactly the same as most of the ones we did in class, but it's the same types of forces that we talked about before, and the one that stays the same is gravity. Gravity's down. Now, normal forces always tend to trip people up, even though we do some examples. People always want to say, well, normal force is up, cancel out gravity. Definitely not in this case. The normal force is the force that stops an object from falling through the surface. So which way is the normal force? Well, the normal force is this way. Because without the normal force, the person would be flying through the wall. Without the wall there to hold them, they would fly out of this ride. So the normal force is this way. That is a creepy looking person now that I put a face on it. Gravity's pulling down, so something must be holding the person up, and it's not a normal force. The wall doesn't hold the person up, at least not the normal force of the wall. What holds them up? Friction. I'm going to say it's static friction because I'm going to assume, you know what, they're not sliding up or down the wall. So these are my forces that act on the person. And if I look at it, well, they're not going up or down, so these forces must cancel each other out, which means what is the sum of my forces? Well, the sum of my forces in this case is the normal force. And which way is the normal force pushing? Well, the normal force always pushes out from a surface. So if the person is here, the normal force is this way. If the person's here, the normal force is this way. And I'm going to draw another one in here just so we can kind of see what I'm talking about. The normal force is this way, and down here the normal force is this way. So we could argue we have a constantly changing force also. Now, it's not changing in magnitude, just like the velocity is not changing in magnitude, but the force is changing in direction. But even though the direction's always changing, here it's down, here it's to the left, here it's up, here it's to the right, even though the force is always changing direction, it does have a set direction to it. What can we say? We can say the forces are always towards the center. So we have this situation. We have this situation where the velocities are always changing in direction. The forces are always changing in direction. And we also know from Newton's second law, the sum of the forces equals mass times acceleration. So certainly in this case, well, the sum of the forces equals the normal force. So if the sum of the force is always towards the center, well, then the acceleration always towards the center. And again, this picture that I'm drawing is not a force diagram, just to say it, because I have one force in there. But now I have a velocity, I have accelerations, I have a lot of things. So it's really just a diagram that's showing all the vectors and how they work. So if the sum of the forces are always towards the center, the acceleration is always towards the center. So these are more observations, if you will, than anything else about uniform circular motion. So when we say something is uniform circular motion, well, then certainly the definition, it's moving in a circle at a constant speed. But along with that, if something is moving in a circle at a constant speed, then we could say these are the types of things that have to be happening. There's a constantly changing velocity because its direction is changing, which means it's always accelerating. But the acceleration is always changing in direction also. It's the only way that it can keep going in a circle is if the forces keep pulling it towards the center. And it doesn't have to be this right? If we think of other things, it's got to be the same thing, a ball on a string. Well, the string always pulls towards the center, right? So, we look at that, the direction that the string is pulling is constantly changing. The velocity is constantly changing. The acceleration is constantly changing, right? So again, we're going back to these situations where everything's constantly changing. And we could see the directions of everything. We didn't really need to do any math. The velocity is always tangent to the circle. the acceleration and the sum of the forces are always towards the center of the circle. So there's a lot of kind of observations that we can make about this. So uniform circular motion, let's kind of say some of them. Velocity is constantly changing in direction. Oops, sorry. Direction. That was a little sloppy, but velocity is constantly changing direction. Again, it's not changing in magnitude. It's still a velocity, but it's changing in direction. And we could say that the acceleration is constantly changing in direction. Actually, let's go back to velocity. It's constantly changing in direction, but always tangent to the circle. Right? I always know the direction. I can pick any place on this circle. If I pick there, assuming I know, right, it's going clockwise or counterclockwise. But if I'm assuming it's going clockwise, well then, what's the direction of the velocity? The velocity is that way, right? I can pick another spot. The velocity is that way. So we always know the direction, but it is changing. Acceleration, and I'm going to lump them together. Acceleration and the sum of the forces is also constantly changing in direction. So it's constantly changing direction, but we always know which direction also, right? Even though it's always changing, it's constantly changing in direction, but always towards the center. So these are things that we know about uniform circular motion. We could establish a direction. We don't really need to do any math to know the direction of the acceleration. We don't need to do any math to know the direction of the forces or the velocity, right? We know that they're always changing, but we could pick their direction at any instant. We could say, okay, at this instant, this is the way they're all going, right? If I pick this direction, this instant here, well, then I know the sum of the forces is towards the center, and I know the acceleration is towards the center. They have to be the same direction because that's Newton's second law. So, things that we know about it. Now, if we have uniform circular motion, this is where there's a new equation introduced, then we can figure out what that acceleration is. We know the direction is towards the center. What's the magnitude? Well, the magnitude depends on a few different things, right? Magnitude depends on how fast you're going. You're going faster and faster and faster. There must be a greater force towards the center to hold you in a circular pattern, right? And the second thing is, if the circle is very big, well then, you know what? You don't have to accelerate so greatly, right? So the smaller the circle is, the more acceleration you must have. So the acceleration we can kind of think about in terms of those things. And again, sometimes in this case, maybe the rotor is not the best example in my mind, but a ball on a string. If we're swinging around a ball on a string, if I swing it faster and faster and faster, well, the string has to pull harder to keep it in a circle, which means the sum of the forces towards the center went up, which means the acceleration went up. There's a greater acceleration. And also, if it's a big circle, well, I don't have to make it go that fast, right? I can, if it's a big circle, well then, even if it's moving fast in that big circle, the tension on the string's not that great. But if I make the circle smaller and smaller, well, now the tension goes up because it's just making it accelerate more. So, new equation. In this case, if we have uniform circular motion, then we have a new equation for acceleration. Acceleration is v squared, the speed squared, not velocity again, because velocity is always changing, divided by the radius of the circle. And we have a direction. It's towards the center. There we go. So acceleration is speed squared divided by radius. Again, it's the new equation. It's the only new equation in this area, but this is a helpful equation because it's going to help us understand the forces that come into play when they're making something constantly change. Now, I want to go back to this force diagram because there's always people saying, well, you know what? This person is moving around and around and around, aren't they exerting a force? And sure, they're exerting a force, right? They're exerting a force on the wall, but that's about it. And people, what they want to do is they want to kind of add other forces to it. They're saying, because they're moving around in a circle, so aren't they pushing in a certain way? And there's two answers to that. Number one is, yeah, sure they are, right? They are pushing on the wall. But I don't care what they're doing, because going back to Newton's laws, we care about the outside forces. We care about what's acting on the person to make them move in a circle. We don't really care about what the person is doing to its surroundings, right? Because it takes an outside force to make something accelerate. So we care about the forces acting on the person. So that's number one. But number two, the other thing is going back to Newton's first law, an object in motion tends to stay in motion in a straight line. And that's the big thing here, right? Which I think sometimes confuses people. So I want to say it a little bit, and hopefully it helps. What I'm saying is when the person is here, they want to go this way. That's Newton's first law. An object in motion tends to stay in motion in a straight line, right? So they want to keep going in a straight line. That's inertia. Now, inertia is not a force, so it doesn't show up on my force diagram, right? They have a tendency to want to go this way. So what does the wall do? Well, the wall pushes this way, which makes them accelerate this way, which makes their velocity gain a vertical component, which makes them to start moving down, which is good, right? And as they get here, well, now there's a force this way, so now they are moving down more, and they're starting to move more. They're starting to accelerate to the left, right? So as this person moves around, we need these forces to make them change what they're doing, right? To make them accelerate and therefore make their velocity change. So there's no force. There is no force this way, right? That force doesn't exist, right? If we go to my drawing, it's simply they have inertia, and this force is what's required to move them out of their straight line path. All right, hold on. There we go. So uniform circular motion gives us a new equation. Now as I'm switching things, I see what's happening. Let me kind of erase these, and then I'll keep going. All right, so what we have now is we have some new measurements when we're dealing with uniform circular motion. And we're going to see that this pops up in other cases, these two measurements. We're dealing with something that we're assuming goes around and around and around in a circular pattern. And that allows us, or that requires us, to get some new measurements. And these measurements will pop up in waves and simple harmonic motion. They'll pop up in other places too. When we have a repetitive motion, we can see these measurements that we're going to be talking about. The first one being period. The other word for period certainly could be time. And we tend to measure in this class in seconds, and it is the time for one complete motion, for one complete motion. So period is the time for one complete motion. Frequency is not time. Frequency is frequency. And we'll talk about the units here in 1 second, but one of the things we say is frequency is the inverse of period. We could say that frequency is the number of complete motions per second. So period is the time for one complete motion. So we could say it takes, like, if we have something going in uniform circular motion, we have the person riding on the rotor, we could say it takes 2 seconds per trip. That would be their period, right? Person was going around and around and around and around and around, and it takes 2 seconds to get from here all the way back around to there, right? That would be their period, the time it takes. Now, the other one, we'd have number of complete motions per second. So if we went around, well, they only did half a trip, right? So it would be 0.5 trips per second. So if we were measuring their frequency and it takes 2 seconds, well, in 1 second they went to here, they didn't do one trip. They did half a trip, right? So trip isn't a unit. So when we just measure it, they say, oh, the period's 2 seconds. But we understand it's 2 seconds to do this thing once, 2 seconds per trip. This one, though, trip's still not a unit, but it kind of makes sense when I put it in there right now. It's 0.5 trips per second. Now, how do I write it? Well, just like here, I don't put trips down because it's not a real unit. Here, I can't put trips down because it's not a real unit, but that's not 0.5 seconds. That's 0.5 per second, right? 0.5 per second. Now, do we write it that way? We tend to not write it that way. We tend to write it in hertz, where 1 hertz, Hz, equals 1 per second. So just I think because people don't like to use this per second terminology, hertz is used, right? So we measure things, frequency of things in hertz. How many trips per second? Now, this is not a hard, fast rule, but we tend to use period when something's moving slowly, when it takes multiple seconds to do one trip. We tend to use frequency when something's moving very fast, and it's going to be a lot of trips per second, right? So we could use either one at any time, and certainly we could see, very small periods or very big frequency. We could see a lot of different things. But that's how they tend to be used in the real world, right? We measure the period when it's something moving slowly. We measure the frequency when it's something moving fast. But again, we can do it either way. Now, with all that said, period is time, so it's t. Frequency tends to be a little f. And again, if we look at these two, they are the inverses of each other. So the time for one complete motion, how many seconds per trip. This is number of motions per second, so this is how many trips per second. So I don't really know if this is a second equation. Some people are like, oh, you gave 2 equations, so there's only one. But time is the inverse of frequency, right? So that just goes by the definitions. All right, let me kind of clear this. Maybe. There we go. So what is centripetal force? Centripetal force goes right along with uniform circular motion. And I think the best way of explaining it is when we say when an object is in uniform circular motion, we can say that the sum of the forces is centripetal force. So the sum of the forces is centripetal force. So when we say, hey, there's a centripetal force, we're already saying, hey, this thing's in uniform circular motion. Or if we say, hey, that's in uniform circular motion, then we could term the sum of the forces as the centripetal force. Not a new force. It just happens to be the name we give the sum of the forces when we're in uniform circular motion. Now, there's a reason why we do this, because we know according to Newton's second law, the sum of the forces equals mass times acceleration. And because we are in uniform circular motion, we also know the acceleration equals the speed squared divided by the radius. So I can now say the sum of the forces equals mass times v squared, speed squared, over r over the radius. So again, some people like to argue, well, that's another new equation. Not really. I just took out the a for acceleration, and I added what the acceleration equals to because we're in uniform circular motion. So if we draw a force diagram, add up all the forces, and we get a sum of the forces, that sum of the forces has to be the same as mass times speed squared over the radius. Again, not a new force. It's the same forces, right? So we're not going to say, oh, now there's a centripetal force in this problem. That's what's keeping it in a circle. No, right? The forces we've already discussed, those are the forces that keep it in a circle. If it was the rotor, well, then it's the normal force equals mv squared over r. If it's a ball on a string, well, then the string tension equals mv squared over r, right? So we're going to find the sum of the forces, we're going to add them up, and instead of making them equal mass times acceleration, we make them equal to mass times speed squared over r. That's the only difference, right? And again, the force diagram should look pretty much like they looked like before. They're going to have the same types of forces because it's not new. All right, so let's look at this rotor. And we're going to kind of go back to it. So we have this situation. This person's going around and around and around. I don't know how much of this we have to draw, but we're going to draw a little bit. And let's look at a video. And then I'm going to kind of come back to that. We're going to keep those for now. And I'm just going to scroll this a little bit. It's not my video, obviously. It's made by this person who's got a lot of subscribers, and this has been watched over 5 million times, which is kind of surprising. Not that great of a video, but maybe people are using this for talking about physics. Who knows? So we have this rotor. I'm not going to show the whole thing, so we're going to go back to 206. We could see people come in, other people can look from the top, and this thing is going to spin around, right? So they're going to move them into place, and then they're going to spin around. We're going to use some of that information. How hard the wall is. Alright, so here we go. They're going around and around and around. You see that the board drops out and they're stuck to the floor. Once I click this one, I'm going to take it one person real quick. Time how long it takes to then go around. This person is blue. Alright, so that's about the same. By my degree of measurement of time, they have a period of 1.7 seconds. It takes 1.7 seconds to go around. You're welcome to try and time it yourself. Just pick a person, start your stopwatch, and then slow down. Alright, so we see this. We see these people going around. Now, again, I'm going to make an estimation. But let's go back to our calculations. There we go. We are going to say that they have a period. Yeah. All of a sudden. I'm going to say they have a period of 1.75 seconds, which I think is pretty close to what they're doing. And the other thing, now this is again an estimation, though my period doesn't seem it's too far off. I mean, we have a video, and as long as it's not moving at some abnormal speed, I mean, anyone can get that time, but I think you should be in the ballpark of me. And then the distance from the center to where they're pressed, or the radius. And I'm going to say that radius looks about 2.5 meters, right? 6 meters is, or I'm sorry, 2 meters is roughly 6 feet. And if a 6-foot person laid down, actually, you know what? I'm going to make that a little smaller, because I think if a 6-foot person laid down, they probably would be touching the center. So I'm going to say that it's about 2 meters. Again, now that's a little rougher one. That's more of an estimation than anything else. But again, if I look at this picture, right? And I wanted that distance. So again, if I imagine like this person laying down, they'd probably cover that span or come pretty close to it. So 2 meters seems about fair. So we have a person that has a period of 1.75 seconds, and the distance or the radius of the circle they're traveling in is 2 meters. Now, we are going to figure out what the normal force is. Now, we have to know a few things about this person, because the sum of the forces equals mv squared over r, because this person's in uniform circular motion. So we're going to get a mass, but we're just going to take a mass of an average person, right? So if I go back, we'll just Google it. Right? Like persons. Maybe we won't. There we go. Person with a mass of 60 kilograms and weighs 132 pounds. We'll go with that. All right. So we have this person. They have a mass of 60 kilograms, just a number I've made up. We took this off the video, 1.75 seconds. And again, we estimated this from the video and from pictures, and we'll say it's 2 meters. So we have this person. Force of gravity is down. Friction is up. And the normal force is in. And if I add this up, I know these two cancel each other out. So the sum of the forces equals the normal force. And because we're in uniform circular motion, it equals mv squared over r, mass times speed squared over r. Now, we have to get the person's speed. That's the one thing we don't have, because what we have is we have a period. We have the time. But we know it's a circle that's 2 meters. So if the radius is 2 meters and they do this all the way around in 1.75 seconds, well, then what do we need? We need the circumference of this circle. And once we know the circumference, well, then we know the distance they traveled and we know the time it took to travel, so we can get that, right? So if I'm thinking about this correctly, well, then I know the speed is the circumference divided by the time. That will give us the meters per second that we're looking for. How many meters do they cover every single second? So what we have to do is we have to know how to get the circumference, 2 pi r, or we could say it's what, pi times the diameter. But this time we have the radius. So 2 times pi times 2 meters gives us a circumference of, come on, there we go, 2 times pi times 2 meters gives me a circumference of 12.57 meters. And if I want to get the speed, well, the speed is circumference divided by time, so 12, there we go, 12.57 meters divided by 1.75 seconds. 7.18 meters per second. They're covering 7.18 meters every single second. Well, now we can do this problem, right? This problem is basically done. I didn't even really ask a question, but we're just going to kind of work through these calculations. But I can figure out the sum of the forces. I can figure out the acceleration. There's things I could figure out. 60 kilograms. Times 7.18 meters per second times 7.18 meters per second divided by a radius of 2 meters. Now look at the units. This is going to cancel out this. I'm going to be with kilograms meter per second squared. So I am going to have something that is in kilogram meter per second squared, which is the same as in Newton. And before I do that, actually, let me erase that. Let me break it up a little bit. It's going to be 60 kilograms times all of this. So if I just deal with this first, I can get the acceleration. What's this person's acceleration? Well, it's going to be 7.18 squared divided by 2. They have an acceleration of, let me change that color back, 25.78 meters per second squared. So right here is our acceleration, right? And that's a pretty extreme acceleration. They're moving pretty fast, right? This is when we start to get into G's. This is how many G's they feel, because we know 1 G is 9.8. So if we divide it by 9.8, they experience 2.63 G's, right? And that question has popped up in log kappa, and right, it doesn't matter what the person's mass is, they experience 2.63 times their normal body weight. The wall is pushing at a force that's 2.63 times the force that they normally feel exerted on them in order to hold them up. If they're laying in bed, well, the bed's holding them up with a force of 1 G. They're going down, their mass times G, and the force that's lifting up is their mass times G, right? Well, this wall has to push much harder than that. So we could figure out the acceleration. We could figure out in terms of G, and this is where kind of this idea of G's makes sense. The wall is going to be pushing harder on them than what they're used to feeling. That's what you feel. You feel this G force pressing against you. But now we can get the actual normal force, because we take that number, multiply it, the 225.78, and multiply it by 60. And I get a force of 1546.9 newtons. That is the normal force that this person feels. So This video is going long, but that's all right. I'm going to make a few more observations about this. Going back to the force diagram. Actually, you know what I'll do? I'll make a duplicate slide, and then we'll erase some of this stuff. There we go. So there's things we know. We know the force. We know the acceleration. We know all these things. I'm going to get rid of a whole bunch of this, and I'm just going to kind of keep this force that we have. And I'm going to keep my force diagram drawing, and I'm going to get rid of everything else. And I'll leave that there because that's just our original measurements. All right. So what else do we know? Well, if I look back with this, I can get the force of gravity 60 times 9.8, so that's a doable number to get. And the force of gravity on this person is 60 times 9.8, force of 588 newtons. We know the normal force in this case is 1546.9, or it's 2.63 times that value. That's what it's telling us. Again, if we did it in terms of G, right? This is the force of 1G, mass times 9.8. This is the force of 2.63, mass times G times 2.63. And I also know they're not sliding up and down, so I know this is the case, 58.8 newtons. So if I was designing this ride, I can start to look at these things. I can say, okay, well, how am I going to make this? Because if I put plastic on the wall, they might just slide right down the plastic, right? We don't really know. So we got to make sure that when they're on this, they don't slide up and down. Because if it was too slippery of a surface and you start going slow, you slide down. Right? If you start going too fast, you might slide a different way. So we do want that person stuck to the wall, right? And that involves friction. So what else do I know? I know static friction is less than or equal to the coefficient of static friction times the normal force. So we can kind of look at this now. We could say, okay, well, the static friction is 588, or it equals mg. And I don't know mu, but I do know the normal force. Well, the normal force equals the sum of the forces, so that equals mv squared over r. So again, kind of a nice observation here when I write it this way, that in this case, the mass doesn't matter, which is good because there's not really certain people that we have to remove. That's a wrong color to watch things cancel out, isn't it? There we go. So I can divide both sides by mass, and mass disappears. Now, I don't have to do it this way. I could just plug in numbers because I know this number and I know this number. So I can just plug in numbers and solve for mu. But I'm just saying, if I didn't know the mass, it doesn't matter. When I design an amusement park ride, I don't say, hey, you're too big for this ride. Hey, you're too small for this ride, right? The only time you're too small is if the harnesses won't hold you in the place, but the ride doesn't care about size. And this is another case where, you know what, everyone's going to stick to the wall unless someone comes in and they grease themselves down. But if you're wearing normal clothes, well, then everything's just fine. So mass doesn't make much of a difference. Now, I'm going to go back and I'm going to do it this way just to save me a little bit. So this is 588 less than or equal to mu static, coefficient of static friction, times 1546.9 newtons, 588 newtons, divided by 1546.9 newtons, and that equals the coefficient of static friction, which is good. Doesn't equal, it's less than or equal to. So this gives me the minimum value of it, is what it's going to give me. So, as long as the static friction is at least 0.38, everyone should be fine. If the number is less than 0.38, then we have this problem where people are going to start sliding down the wall instead of staying stuck to the wall, right? So we definitely have to make sure there's a surface that is rough enough or sticky enough, however you want to term it, so the person doesn't slide down, which means the mu value has to be above 0.38, assuming that this is the radius of the ride and this is how fast it takes to go around one trip, right? These two things are crucial. This, not so crucial for the question that I'm asking now. Right? I could have written this a different way, and I could say that gravity times the radius divided by the speed squared is equal to the minimum value of the coefficient of static friction. So we're still looking at forces. We're still looking at forces the same way we looked at them before, but really what this is doing is this is giving us some new equations to work with, right? It's giving us, well, a new equation. It's giving us this equation to work with, which allows us to do some more calculations that we simply wouldn't be able to do in a different way. Okay, so that is the start of centripetal force. We will look at some other examples in the next video.